The topics for the exam are on the web. You click on schedules and you can see the topics as we cover them at the various lectures. There is no way that I can cover all of these during one exam, and there is no way that I can cover them during this exam review. What I do not cover today can and probably will be on the exam. And not all that I cover today will be on the exam. I have to make a choice, and I made my choice. I want to start with a traveling wave in a string. And that the string has tension T, mass per unit length mu, and let the traveling wave have a amplitude A. So here is the traveling wave, and this amplitude is then A, and the speed of propagation is V. And this V is the square root of T divided by mu. That follows from the wave equation, but I'm not going to address that issue now. I want to deal with energy, and I first will write down the equation for the traveling wave. If this is the x direction, and this is the y direction, then y as a function of xt would then be the amplitude A that you have there, and then you can write this down in many ways. I will write it down as the sine of k times x minus vt. If you want to write down for k v omega, that's fine too. I have no problems with that. So the idea now, what is the energy in one wavelength, say? There are two parts to it. There is kinetic energy and there is potential energy. The kinetic energy is not because the wave is moving in this direction. There is no material moving in this direction. The material is just moving up and down. That's all it's doing. So the kinetic energy is due to the motion in the y direction. There is potential energy due to the fact that I have to give this straight wire, this straight string, a shape. And in order to give it that shape, I have to do work. There is a tension, and I have to stretch the string. That's why I have to do work to give it that shape. So it comes in two parts. And I will only do the kinetic energy part, and I will leave you with the potential energy part. I slice out here a section dx. And so the mass in that section dm is mu times dx. And so the little bit of kinetic energy, K stands for kinetic energy, in this small part is 1/2 times the mass, 1/2 mv squared, and v is the speed, the velocity in the y direction. If the wave is traveling in this direction, this material here is going up. A little later it will be more to the right, and so this is going up at this moment in time. So I can write for this 1/2 times mu times dx, and for Vy I can write then dy dt squared. And so the question now is, what is dy dt? Well, that's easy because we have the function there. So dy dt equals, so first I get A, then out pops a k, then out pops the minus v, and then the sign becomes a cosine. Cosine k times x minus vt. But I have to square that. So I have a square here, and I get a square here. So dk can now be written as 1/2 times mu, and I will leave the dx all the way at the end, and so I'll get a squared, I will get k squared, I will get v squared, and I will get the cosine squared of k times x minus vt, and then at the very end I get my dx. And I now want to know how much kinetic energy there is in one wavelength. Because the total amount of energy, if this is infinitely long, is of course infinitely high. So I'm interested in the amount of kinetic energy for one wavelength. And so that k then is the integral of this whole thing from 0 to lambda. So that now is no longer dk, but that now is k, provided that you realize that it is k kinetic energy per unit wavelength, dus per wavelength. So I only do it for one wavelength. All right. So I get 1/2. I'm going to get here a mu. I get an a squared. I'm going to write down for k 2 pi divided by lambda. So that becomes 4 pi squared divided by lambda squared. For v squared, I'm going to write down t divided by mu. Remember, the velocity was the square root of t divided by mu. And now I have to do the integral of this cosine squared dx between 0 and lambda. And you will take my word for it that this is lambda divided by 2. And so I have to multiply. So the integral, that's the only one that I have to do, these are constant, is lambda divided by 2. And if you look now, you lose a mu, your 4 goes, and you lose even 1 lambda, and so you get a squared times pi squared times t divided by lambda. That is the kinetic energy per wavelength. So I will leave you with the potential energy. It's a similar derivation, but now you have to deal with work that you have to do. And what comes out is perhaps a bit of a surprise, that the kinetic energy is exactly the same as the potential energy. Not at all obvious, but that's the way it works out. So that means that the total energy per wavelength, so now I write down E total, again per wavelength, WL stands for wavelength, not for Walter Lewin, but for wavelength. The total energy per wavelength is now twice that, so it's 2a squared times pi squared t divided by lambda. Now suppose I am generating this wave. I'm standing somewhere and I'm wiggling this. Then I have to generate this energy for every period that I go through, because in one period I generate one wavelength. So if I divide this by the time for one oscillation, then I have the average power over one oscillation. Now the period of an oscillation we normally call t, but I don't want to have another t because I already have a t, so I call the period of the oscillation 2 pi divided by omega, which is the same as the period. And so the power, then, the average power that I have to generate if I am driving this traveling wave into the string, the average power is then E total, and you have that here, divided by 2 pi by omega. And this is in watts, of course. This is joules per second. If now we turn to standing waves, the situation is very different. So here I have a standing wave. There are nodes here. And at those nodes, the string does not move. And let's assume that the maximum displacement is A. Again, the tension is T, mu is the same, but when it comes to a halt, the maximum displacement in the center here is then A. And the question now is, how much energy is there in a standing wave? So this was a traveling wave, this is a standing wave. Well, at this moment in time, when it comes to a halt, there is no kinetic energy, there is no movement in the y direction. So the total energy that is in the wave, per wavelength, is the same as U maximum. But of course, it's also the same as K maximum. When this thing goes through its equilibrium, when the when the string is straight, then you have the highest velocity. This comes down, has a velocity in this direction. This comes up, has a velocity in that direction. That is then the maximum kinetic energy that you can have. So E total is U max is K max. And so we already know what U is. So all we have to say now is that that is the same as A squared times pi squared times T divided by lambda. And so you see a traveling wave with the same amplitude as a standing wave. A traveling wave has twice as much energy per wavelength. And as far as power is concerned, well, you have two waves going through each other, and so you have a reflection from the other side. So you really don't have to do anything anymore to drive the system. You just gotta let it sit. If there's no energy dissipation, the standing wave will just support itself. So you do not have this power that you have to continuously put in, because in the case of a traveling wave, you are continuously generating a wave that moves away from you. That is not the case with a standing wave. It's generated at one point in time, it reflects, and it maintains itself. Now let's turn to electromagnetic traveling waves. Electromagnetic traveling waves, I take plane wave solutions. In its most general form, E as a function of x, y, z, and t can be written as an amplitude, but this is in three directions, so it has an x component, a y component, and a z component. And then I can write down here, say, for instance, the cosine of omega t minus k dot r. This is a dot product. And the meaning of k is called propagation vector, is kx f roof, x roof, plus ky y roof, plus kz z roof. The magnitude of k is the square root of kx squared plus ky squared plus kz squared. Lambda is 2 pi divided by that k, and omega equals k times v. And if it is in vacuum, then v is the same as c, of course. But v then is c divided by n, if you have a dielectric. The index of refraction n for a dielectric is then square root of kappa E divided times kappa m. Most substances, kappa m is very, very close to 1.000, except for ferromagnetic materials. Kappa E itself is frequency dependent, and it can sometimes be extremely strongly dependent on frequency. That's where the dispersion comes in. R equals x roof plus y roof plus z roof. That is the position vector. If you wanted to know what the associated magnetic field is associated with this electric field, then your best bet always is that the curl of E is minus dB dt. So if you know that whole function in x, y, and z, you can take the curl of E. Sometimes it's time consuming, sometimes it's fast, depends on the wave. And then you have to do an integral in time to get the B vector. And what comes out of this is actually something that I do remember. There is very little in physics that I remember. This is one of the things that I remember, so that I don't have to apply every time Maxwell's equations when I solve these problems. And what I remember is what I wrote down earlier, point by point on the blackboard. For traveling waves, E is perpendicular to B. E and B are both perpendicular to K. So E and B are perpendicular to K. Therefore, E cross B, let me give that unit vectors, E cross B is K roof. The Poynting vector, remember, goes in the direction of K. The magnitude of B at any moment in time in a traveling wave is the magnitude of E divided by V, which can be C, of course. And then, and this is key, and I want to stress that, E and B are in phase with each other, in phase in space, and in phase in time. And what that means is the following. The location where E reaches a maximum is also the location where B will reach a maximum, and they reach it at the same moment in time. So if you are somewhere and you find that the E vector reaches a maximum, then you know that the B vector at that moment will also reach its maximum. And if you are somewhere in space where E is 0, you can be sure that B is also 0. That is the case for traveling waves. The Poynting vector S is E cross B divided by mu 0, and if there were magnetic material, you would also have a kappa m here, but I will leave that out. You can write down for the magnitude of B, you can always write down E divided by V. This Poynting vector, of course, is time variable because E itself varies with frequency omega, B varies with frequency omega. So the Poynting vector is, of course, time dependent. And so the magnitude of the Poynting vector you can also write down then as the E squared value divided by mu 0 divided by V, because the B can then be replaced E divided by V. Since they're at 90 degrees relative to each other, I can ignore the cross because the sine of the angle is then 1. If E is a sinusoidal function, for instance, E0 times cosine omega t, then it's clear that you get here the square, E0 squared times the square of cosine omega t. If you time average that, I mean, this S is variable in time, but if you just want to know what the time average value is, then the time average value of the cosine squared equals 1/2. And so you can also write down then that S, I will write it down here, S time averaged would then be E0 squared, this is now the amplitude, divided by 2 mu 0 times V. And the 2 comes from the fact that the average value of cosine square omega t equals 1/2. And this is then in watts per square meter. So that's the traveling wave. Now, I want to go to standing waves. A standing electromagnetic wave, just like the one on a string, has a separation of space and time. Let us suppose we take a specific example. We have here coordinate system. I will call this X, call this Y, and call this Z. Suppose we have linearly polarized radiation, but I'll make it a little bit more difficult than normal. I will linearly polarize it in the YZ plane. In other words, the E vector would be like this then, and oscillating back and forth in this plane perpendicular to K. So the standing wave, E, as a function of x, y, z, and t, can then be written as this vector, that this here would be E0y at its maximum, this would be E0z at its maximum, so that's the one that comes first. So you get E0y in the y direction plus E0z z in the z direction. That is the direction of that E vector. And now you get your spatial part in the x direction, for which you can write down either the sine of kx times x, or if you prefer a cosine, I have no problem with that. And then we have here cosine omega t. There is no dependence of E in y and z, the plane waves. So if you take any plane perpendicular to x, infinite in size, independent of y and z, the E vector will be the same. And so therefore, k of y is 0, and k of z is also 0. So there's only a k of x, and so k then equals k of x, and so lambda is 2 pi divided by this value then. And omega divided by that k, omega divided by this k value, I write an x, but you can leave the x out, would then be v, or it could be c, of course. If you're interested in knowing what the B field is, you go to the curl of E is minus dB dt. The fact that we have here the spatial part separated from the time part means that there are locations for x which never change, whereby the E field is always 0. That's typical for a standing wave. And in this case, they will be nodal planes. The whole plane perpendicular to the x direction, I will draw one here, and I will draw another one here. The E field in that whole plane at all moments in time will be 0. That's the case when this sine, or whatever the cosine you have chosen, happens to be 0. And so these are nodal surfaces. And of course, the anti-nodal surfaces fall right in between. It is not so easy to draw now for you what you will actually be seeing in terms of this sinusoidal wiggle that goes like this. That is not so easy to do. Because the wave will be in the plane that is coming out like this. And it's difficult to show you that in a three-dimensional way. But I will make an attempt nevertheless. So it will be in this plane that is tilting forward that you'll then have nodes and antinodes, and they oscillate like this. Any plane perpendicular to x at any moment in time will see exactly the same thing. Now it's interesting to compare our list with the traveling wave. Again, with the standing wave, E is perpendicular to B. It is not too useful to talk about direction of propagation, because there are really two waves going through each other, so the whole idea of k vector is a little bit bizarre. B, however, the magnitude of B, the maximum value will be E divided by V. The maximum possible value of B is E divided by V. But now comes the big surprise. E and B are 90 degrees out of phase in space and time. So if you have here the nodal planes for E, those are the antinodal planes for B. And where you have the antinodal planes for E, you would have the nodal planes for B. So they're 90 degrees out of space and out of time. So no surprise, of course, that the average value of the Poynting vector is then going to be 0. And that, of course, can also be seen when you think of it, that there's a traveling wave in this direction and a traveling wave in this direction. So there's sort of energy flow in this direction and energy flow in this direction, and the time average will obviously end up to be 0. But if you simply take that E cross B and you time averages, you will see that immediately. This is the consequence of the 90 degrees out of phase and 90 degrees out of space and time. All right. Now I would like to pursue this with, I can either clean the blackboard or let me go to the other side. I'm going now to charge accelerated charges. So here, say, call that the y-axis quite arbitrarily, and here we have the z-axis, and I accelerate a charge q here with acceleration a, and I do that just in the z direction. And I am watching at a certain distance. My position vector is r, and I'm watching here. And this angle is theta. If this charge is a positive charge, and there is a sudden acceleration, a little later in time, I will see an electric field. There's a traveling wave going in my direction. It's not a plane wave, but there is a traveling wave going in my direction, in the direction r, and so that E vector then is in this direction. I will return to this. It's in the opposite direction as A perpendicular. This vector, which is the component of A perpendicular to r, is called A perpendicular. If Q is positive, then this E vector is in the opposite direction of A perpendicular. The E vector that you experience at time t is then minus Q times A perpendicular at time t prime, because the acceleration took place earlier than when the signal arrives where I am, because it takes time to travel. In other words, t prime equals t minus rc. This is the time that it takes for the signal to reach me, and so t prime is earlier than t. And then we have this divided by 4 pi epsilon 0 r, and I believe there is here a c squared. Yes, there is, and this is in volts per meter. Now A can easily be some amplitude times the sine of omega t. In other words, I can oscillate this one up and down harmonically. Clearly, when I do that, I will get an electric field that will also oscillate here harmonically. You really do not get plane wave solutions, because in any direction that you look, you can change the r vector, and you have here the answer, what you see, the E vector. So there is really no such thing as a plane wave solution. If you're far away, you can probably approximate it by a plane wave. The associated B field has all the ingredients that we are familiar with. It's perpendicular to E, and the B field must also be perpendicular to the direction of propagation, which in this case is r. And E cross B will also be in this direction. And if you take all that into account, then you can write the B vector as the unit vector in the r direction times E divided by c if it is the speed of light, c if it is in vacuum, and that is then at r t. So that's the connection between E and B. So now comes an interesting point that we have stressed before, and that is that A perpendicular depends on theta. A perpendicular is A times the sine of theta. It is this component. And so you see that the magnitude of the E vector that you will see when you look at that charge will depend on where you are in space. If you happen to be at theta 90 degrees, you will see the maximum E possible. If you happen to be in this direction where theta is 0, you won't see any electric field. And so there's a very strong dependence of the magnitude of the E vector in the direction. And the same is true for the B vector, because the B and the E vector are always married to each other, so they get the same sine theta. So the pointing vector is now going to be proportional with sine square theta, because you have an E and you have a B. I would like to summarize for you, in the same way that I did that here, what I would like you to remember, it's simply, I will raise this later again, because I want to work at a height so that you can see what I'm doing. So a summary which is very good to remember is that E is in the plane through R and A. In the plane does not mean into the plane. It's in the plane. So look here. The plane through A and R is the blackboard. And therefore the E vector is in the blackboard in this case. So that is key, that E is in the plane through R and A, not into the plane. And E is perpendicular to R. Notice I have that. And E, amplitude, is proportional to the amplitude of E perpendicular. And therefore, it is proportional to the sine of theta. E itself is proportional to 1 over R. Notice that, not 1 over R squared, but 1 over R, which is obvious. It has to do with the conservation of energy. If you make your sphere around it, then the energy that flows through the sphere must be the same no matter how large your sphere is. And since that energy comes from the Poynting vector, has an E cross B, E is inversely proportional with R, and B is inversely proportional with R, so that energy is conserved. So the Poynting vector will then be inversely proportional to R squared. If you're interested in the total power, so you're not interested really in the fact that the Poynting vector is a strong function of theta, namely sine squared theta, but if you integrate the Poynting vector over one sphere that you choose, and you take the local Poynting vectors, and you multiply that by the local areas, which becomes an integral, then you can actually come up with a power. This is now in joules per second. In other words, you tell me what Q is, you tell me what A is, you are creating electromagnetic radiation, I will tell you how many joules per second work you have to do. And that then becomes, that's called the Larmor result, the Larmor equation, and that becomes Q squared times A squared divided by 6 pi epsilon 0 c to the power 3. Notice there is no R anymore, because clearly it's independent of where you are in space. That's the how many joules per second you have to generate. It's obvious that it is proportional to Q squared, because E is proportional with Q, so B is also proportional with Q. So the Poynting vector will be proportional to Q squared. It's also obvious that there is an A squared, because E is proportional to A perpendicular, but nevertheless A, and B is also proportional to A. So it's no surprise that you get there upstairs a Q squared and an A squared. Now, if A is oscillating, if A is A0 sine omega t or cosine omega t, then you can calculate what the mean value of the power is during one oscillation, and then you will get here the average value of the sine square omega t then becomes 1/2, of course. This is the energy that you have to generate per second in order to create electromagnetic radiation. It is not the kinetic energy that you have to put in the mass of the charge, the 1/2 mv squared. That's a whole different story. This is the price you pay for creating electromagnetic radiation. Several students have come to my office and asked me, why is it, apparently I wasn't clear enough, why is it that when you have Rayleigh scattering, and when the light scatters at 90 degrees angles, that even if you have unpolarized light that you start with, why is it 100% linearly polarized? If and only if it scatters over 90 degrees. And so that is indeed an important point, so I will expand on that in a way that is perhaps easier for you to digest. Maybe I went over too fast when I covered that in class. I demonstrated it. You remember I did it with the smoke signal and I did it with the sunset. So we have unpolarized radiation. Let's first agree what is unpolarized radiation. There's a beam of light coming straight at you, and it's unpolarized. The first plane wave, I think of it still in terms of a very classic 19th century idea, plane wave solutions. The first plane wave is linearly polarized like that. The second one is linearly polarized like that. Then there's one like this, then there's one like this, then there's one like this, one like this, and one like this. It's a zoo of everything. That's unpolarized radiation. Okay. I pick one of those. Right here, this one, and here happens to be fine dust particles which have electrons, and these electrons are shaken up and down by that electric field. So what I'm drawing now here is the motion of that electron. The electron is going to be accelerated in a harmonic fashion. And where are you? Well, you are here. You're looking. And this angle is theta, the same angle theta that I had there. What will you see? E is in the plane through R and A. Ah, so it's in the plane of the blackboard. So the radiation comes straight at you, but here is all of a sudden this electron, a bunch of electrons that go like this, and I am looking, I'm happy to be sitting in the plane of the blackboard, because that's 90 degrees, right? When the radiation comes like this, then the blackboard is 90 degrees. Whether you hear it's 90 degrees, this is 90 degrees, this is 90 degrees, that's also 90 degrees. This is not 90 degrees, but that all is 90 degrees. Radiation comes in like this, whoosh, and I'm looking there. But it is in the plane through R and A, so it is in the blackboard. It is perpendicular to R. Ah, that's nice. So it's linearly polarized. Do we agree? Linearly polarized. Now, there's another one that comes in. This one comes in. Okay, there it is. This one comes in. Starts to shake the electron in this direction. I am still where I was before. I'm here. Same location. This angle now is theta. So the second plane wave comes in like this. What do I see here? E vector is in the plane through R and A. Ah, that is the blackboard. E is perpendicular to R. Ha! So I see this. Do I see the same strength of the E vector? No. It's much less. Because A perpendicular is much less, because theta is much less. But I will still see E vector in this direction, following my recipe. And then there is one electromagnetic wave that comes in, which happens to be in this direction. Well, in that case, I will see nothing. That is tough luck. But any other direction, you will always see electric vector perpendicular to your line of sight. And that is only true for 90 degrees. In other words, if I made a circle here, and I have unpolarized light coming in here, straight at you, when you hear and you look down, you will see the E vector like this. When you hear and you're looking down, you will see an E vector like this. If you look here and you look in this direction, then you will see the E vector like this. And this is only true if you are at 90 degrees angles. I can easily make you see that if you change the angle, that it is not 100% linearly polarized. And the best way for me to show that is, here are these electrons, which are being shaken like this. One comes in, shakes like this. And let's look now at forward scattering. Not 90 degrees, this is 90 degrees. Forward scattering. Here's the electron going up and down. You're sitting there in the audience. If this one comes in, you'll see electric vector like this, generated by this charge, which goes like this. Now the next one comes in, which goes like this. you will see an E vector like this. The next one will come in like this. Forward scattering, you will see like this. So you see, if unpolarized light comes in forward direction, it remains 100% unpolarized. In any other direction, it will be partially polarized, but in the 90-degree direction, it is 100% linearly polarized. That is the reason why the sky, 90 degrees away from the sun, is 100% polarized. And I check that almost every other day to make sure that physics still works. It's great fun. You take your linear polarizer. I always carry a handful with me. You look at the sky 90 degrees from the sun, and indeed, the sky is practically 100% polarized there. Quite amazing. I have a movie which is not the greatest movie. I tried to show this to you earlier. It's not the greatest. It's trying to make you see that when you oscillate charges back and forth, that something happens in the E field, that you get in the E field kinks. And students have asked me more than once, why do you only get kinks, and therefore electromagnetic radiation, if you accelerate them? Why don't you get kinks if you simply move them with a constant velocity? And I think the best answer that I can give is the following. Think of the electric field lines as spokes, rigid spokes, which are attached to the charge. So they're attached to the charge. They're rigid, but they are fragile, like spaghetti, but they're rigid. And so they move with constant velocity. So all these spaghetti moves with this charge, they all have the same velocity. There is no stress anywhere on the spaghetti because the whole thing has the same velocity. Now all of a sudden, I take the charge and I accelerate it. Now the spaghetti feels a kink. The spaghetti feels all of a sudden it wants to break because the spaghetti is very fragile. And that break caused the kink in the field line. So that's the best way that I can convince myself why a constant velocity does not cause electromagnetic radiation, but it's really the acceleration. Some students thought when I used the word spaghetti that I meant cooked spaghetti. No, I didn't mean cooked spaghetti. I meant uncooked spaghetti, which is very brittle, which easily breaks just like this. And when you accelerate all of a sudden the charges, these field lines can break like uncooked spaghetti. And this movie is making an attempt. It's not the best thing, but we'll make an effort. So Marcos, if you can do the honors there, then I will do the honors here. And you may not get much out of it, but at least it is an attempt. Were we going to give it TV, or are we going to make it completely dark? TV. If you wait a second, then I think the part that I want to show. Okay, so oscillating charges. So it oscillates, but the speed is constant. So it's instantaneous fast acceleration. And then the speed remains constant. And you see these shells here, which are then representative for the electromagnetic radiation. It's not harmonic yet. We're going to shake them harmonically shortly. And so these lines that you see are the field lines. And they are just here in these shells. They are broken. It's broken spaghetti. Also notice that it's like a spherical wave. It's nothing to do with plane wave solutions anymore. You really get a spherical wave going out. It's not so clear from here that the strength of the wave is very different for the different directions of theta. That's not so clear. And so here you have a simple harmonic motion. This is about 1 Hertz electromagnetic radiation. Have you ever heard of that, 1 Hertz? We're dealing normally with megahertz and gigahertz. This is very slow motion, but it's simple harmonic. And you begin to see that indeed there are electromagnetic, these are the E field lines, that they are being distorted in the direction perpendicular to the direction of your line of sight. Is it a great attempt? No, but it is an attempt. So I think this is a a good moment for a break, perhaps a little bit early, and we will reconvene in 5 minutes so you can warm up. Okay. I will now tell you what I will not talk about, which is a lot. I will not discuss Fourier analysis. That doesn't mean that it will not be on the test. Make sure you're familiar and comfortable with the examples that I had in the problem sets. I will not cover today Doppler shift. Make sure you feel comfortable with Doppler shift. It's not a very difficult subject, but it has very far-reaching consequences, as we discussed, including cosmology and black holes. I will not discuss Fresnel equations, even though they are very crucial. They were at the center of my lecture earlier this week. I will not discuss Snell's law. I will not discuss today the Brewster angle. But don't be surprised, don't be shocked if there is a problem related to the Brewster angle. I will not discuss critical angles, total internal reflection, but it may be on your test. And I will not discuss today radiation pressure. That doesn't mean that it will not be on your test. It's simply not possible to cover all of this in the available amount of time. Now, of course, I have not left out purposely things that will be on the test. A lot of stuff that I have covered today will be on the test, of course. But there will also be stuff that I covered today that will not be on the test. I want to discuss now one of the bizarre dispersion relations that evolve from the boundary conditions of electromagnetic wave on ideal conductors. And we spent a lot of time on the demonstration whereby we had two parallel conducting plates, and these plates were separated in the x direction by a distance a. This is the y direction, this is the x direction, and this is the z direction. And I want to propagate through these plates, which are infinitely large in the y direction, infinitely large in the z direction, at least very much larger than the wavelengths. I want to propagate electromagnetic radiation which is linearly polarized only in the y direction. So that is what I want to do, and that's what I demonstrated also. Well, K, this is beginning to be boring now, it's Kx times x plus Ky y roof plus Kz z roof. And the K, this, by the way, is 0 because there's no dependence of the E field in the y direction. So Ky is 0. So K is the square root of Kx squared plus Kz squared. Omega is K times V. Let's assume this is in vacuum. So omega is K times C. The boundary conditions demand that at x equals 0 and at x equals a, this component must vanish, because you cannot have an electric field in the surface of an ideal conductor. That was one of the boundary conditions that we derived. In other words, E of y must become 0 for x equals 0 and x equals a. And as a result of that, you're going to get a standing wave in the x direction, and you're going to get a traveling wave in the z direction. And the boundary conditions demand now, in order to meet this, that the k of x is going to be m pi divided by a. If then you have your wave, then you will see substituting for kx, this value will always give you then, if you have the sign of kx times x, always a 0 here and always a 0 there. And so omega will then be c times k, so is c times the square root of m pi over a squared plus k of z squared. And this is what we call the dispersion relationship. This equation is responsible for a bizarre behavior. And the bizarre behavior then can best be shown in a diagram which we call the omega kz diagram. I will raise this later again because I want to work over my head so that you can see what I'm doing. So this is kz and this is omega, and I am going to plot for you this relationship. This line would be omega equals kz times c. That would be non-dispersive. However, this is different because of this. And so now you have here a frequency which is the lowest frequency possible for which radiation can actually go between the plates. And this then is the case for μ equals 1, and omega is then c times pi divided by a. And so here, for omega, that is the cutoff frequency, is pi times c divided by a. And if I plot then that curve, you get something like this. So no frequency below that value can propagate through the gates, so to speak, through the opening, because it cannot meet then the necessary condition that the E field becomes 0 here and 0 there, which is non-negotiable. It has to become 0 here and it has to become 0 there because it's an ideal conductor. So K of x must obey this boundary condition. So let us assume that at a particular moment in time, we have a frequency going through these two plates, the frequency of this linearly polarized radiation in the y direction, and that this is the value for omega. That means that the associated value for kz is then this. Kz must adjust itself so that kx can remain what it has to be. This line, everywhere on this line, kx is the same value. And the kx value everywhere is pi over a. And so kz is being slaved to become the value that meets this dispersion relation. And that's this line. So kz settles there. The phase velocity in the z direction, v phase in the z direction, is omega divided by kz. Well, look what that means. Omega divided by kz. So I can draw a line here. And so this angle is an indication for the ratio omega divided by kz, which is larger. This angle is higher than this one. And this was c, remember? And so you see that that value is always larger than c. You can just see that by looking at the graph. The group velocity in the z direction is d omega dkz. And d omega dkz is the tangent along this line here. So at this point here, the tangent would be like this. I don't want to draw another line because it becomes too cluttered. But you can see that this slope is smaller than the line here, which indicates the c. And therefore, the group velocity is smaller than c. So this is smaller than c. If you lower omega and gradually reach your cutoff frequency, below which you can no longer propagate any radiation between the two plates, then you get a situation which becomes even more bizarre, that when you reach that point, nothing will go in the z direction anymore. Nothing will come out. I demonstrated that. The group velocity will therefore have to become 0. Well, you can see that because the tangent on this slope here becomes horizontal. So the group velocity indeed right here is 0. But the phase velocity is infinitely high. Think about it, because kz now becomes 0. And so you get an infinitely high phase velocity. And I spent quite some time during my lectures to explain to you why that has no physical meaning. I don't want to go over that now. There is no such thing as resonance frequencies. Often you people think that these are resonances. No, it's not a resonance at all. It is a mode. It means that if you have radiation at this frequency, that in the x direction, kx will adjust itself such that you get a standing wave in the x direction. In this case, you get something like this. Nice little sinusoid, 0 here and 0 here. That's for m equals 1. And kz will then, whatever it has to be. And so when you change omega, kz will adjust all the time. If you go to very high frequencies, there is here another cutoff frequency, which is twice this number, because that is when Mary equals 2, and when kz becomes 0, that becomes twice as high. Then, of course, there are two different ways that you can propagate radiation in the z direction. Because now you have here the line, and if now your omega is high enough, then you get an intersection with this line, and you get an intersection with that line. So that allows you for two different values of kx and two different values of kz. It's not a resonance frequency. Nothing is resonating. It's a mode, but it's not a resonance mode. It's not a normal mode in that sense. Now, the most interesting thing for me is, and I stress that when we discussed this, and I even demonstrated that, we did this with radar, remember, with the 10 gigahertz transmitter, the 3 centimeter waves. The most interesting thing is that if you reach omega equals omega c, and you can do that by, we had a 10 gigahertz transmitter, and we made a smaller and smaller and smaller, and when a became less than lambda over 2, that means omega became less than omega c, then no radiation will propagate through anymore. And so what we did, the demonstration was, we started out, we had lambda was 3 centimeters, and we started out with a gap of about 2 centimeters, and radiation went through, and the moment we hit the 1.5 centimeters, it stopped abruptly. The interesting thing now is that if your radiation is only linearly polarized in the x direction, there is no such problem. There is no such thing as this crazy dispersion relationship. Because an E vector being perpendicular to this plate and being perpendicular to this plate is no problem. If the E vector oscillates with frequency omega, always perpendicular to those two plates, the only thing that happens that nature, like crazy, adjusts the local rho s's, the local number of coulombs per square centimeter, so that you always meet the normal boundary condition. But nothing ever has to become 0. And so therefore, there is no boundary condition that gives you rise to such a crazy dispersion relationship. So if you had radiation linearly polarized in this direction, then it would follow this line. Non-dispersive. Phase velocity is c, group velocity is c. So now comes the interesting part. Suppose you manage to get radiation which is unpolarized. And this you try to send through there. And you make A smaller than lambda over 2. That means that the vertical component of the E vector of each one of those waves cannot get through. Only the horizontal component can get through, but without any difficulty. Speed of light. That means you have created linearly polarized light out of unpolarized radiation. I wouldn't say light in this case, you know, it's radar. So if you could manage to get unpolarized radar going into this direction, and you make A smaller than lambda over 2, all components in this direction are killed, only this component can go through. And so you have created at the other end linearly polarized radiation. And I realized that after I gave that lecture, how cute that is actually, that this is a way in principle that you can create linearly polarized radiation simply by squeezing it through a very narrow opening, a very narrow tunnel, so to speak. The mother of all demonstrations was the sound box. That will go into history as one of the greatest demonstrations ever. This was the X direction, size A. This was the Y direction, size B. And this was the Z direction, and I gave that size C. Some of you thought that it was D, but it's really a C. And we have sound. And this box is closed on all sides. I'll write down an A here. Read me. So the box is closed on all sides. That means, if we think of the pressure, there must be pressure antinodes at all surfaces. The particles, the air particles, cannot go beyond the wall, so they can push on the wall, they can suck on the wall, they can push on the wall and suck on the wall. That means antinodes in pressure. And there have to be antinodes on all walls. So I can write down the pressure, P, that is the pressure over and above 1 atmosphere, as some amplitude P0 times the cosine of Kx times x times the cosine of Ky times y times the cosine of Kz times z times cosine omega t. And the reason why I already pick cosines is because I know that I want the antinodes when x equals 0 and when x equals a. I want the antinodes when y equals 0 and y equals b, and the same for c, for the z direction. And so the boundary condition now demands that kx can now only have unique values, discrete values, which is L pi divided by a. Ky can only be Miri pi divided by b, and Kz can only be Nancy pi divided by c. If not, then the boundary conditions are not met, and then I don't have antinodes at all the surfaces. And L, M, and N can be 0 or 1 or 2 or 3, including 0. Make one of those 0. There's no sign here. If you have a sign there and you make it 0, then everything becomes 0. But if you make a cosine 0, then it's 1. So 0 is allowed, except they cannot all 3 be 0, and you will see very shortly why. So omega, which is always k times v, v is the speed of sound, so omega equals v then times the square root of L pi over a squared plus m pi over b squared plus n pi over c squared. Omega has then unique values. Now we are dealing with resonance frequencies. Completely different from there. There were no resonances there. These are the unique discrete resonances, L, M, and N. And now you can see why you cannot make them all 3 0. Well, because then you have omega equals 0, and that's not a very interesting thing. So now comes the question, what is the lowest possible frequency that is the resonance frequency, the lowest resonance frequency? Well, that depends on which dimension, A, B, or C, is the largest. And so if A, for instance, were 10 centimeters, and if B is 20 centimeters, and if C is 50 centimeters, which happens to be 0.5 meters, then clearly the lowest frequency is L0, M0, N equals 1. 0, 0, 1. For the 0, 0, 1 mode, I then get a frequency F, which is omega divided by 2 pi. And that means I lose all these pi's here, by the way. And so I get a V divided by 2C, that is my C. Because look, if I make Nancy 1, my pi is gone, so I only have a 1 over C squared. This is 0, so I get 1 over C, and the 2 comes from this. So the frequency, that is the lowest possible frequency, is V divided by 2C. C being now half a meter, and so if V is 344 meters per second, then the lowest frequency is 344 hertz. And I proudly demonstrated that to you. Our prediction was accurate to better than 1 hertz. We had exactly the 344 as the lowest possible frequency. And then, of course, you can look for higher order frequencies. And that depends then on the dimensions of A and B, whether the next one is 002, or whether the next one is 011, or whether it is 101. And we ranked them all, and I showed you 8 of those frequencies. And we had a handout, at least on the web. I showed you these wonderful resonance curves that we generated during our lecture. I think it was lecture number 16. You can still download it from the website. Now comes an interesting question. What would happen if I knock out this panel in front and the panel in back? So I knock out both panels in the z direction. So I make it open in the z direction, open at both sides. What happens now? Well, the pressure now can never be an antinode at z equals 0 and at z equals c. On the contrary, it is connected with the universe. No pressure differential can ever build up. So the pressure has to become a node now for z equals 0 and z equals c. Well, that we can easily do. We just change the cosine into a sine. And nothing else changes. Because look, if now I make kz n pi over c, then you will see for any value for n that you choose, this will indeed become a pressure node. You will get 0. And so this now is the right solution then, when the panels in the z direction have been removed. The only thing that you cannot you cannot allow n to be 0. Because if now you make n 0, then no mode could exist. Because if n is 0, then this would always be 0. So now you have a situation that, yes, L can be 0, n can be 0, but n cannot be 0. So what now is the lowest possible frequency? It's the same, 001. And so the lowest possible frequency when you break out, when you make it a tunnel, is again 344 hertz. And that was quiz number 9. I asked you for this one, which was, of course, a giveaway. If you attended that lecture, you could not possibly have forgotten that. Because I made I was almost crying when I showed you this demonstration. So you couldn't have forgotten that I was crying. And then I just wanted to test your insight that you realize that the antinodes become nodes, but that nothing changes. At least not in terms of resonance frequency. Of course, something changes in the box, of course. Because now you have 4 walls where you have pressure antinodes, and you have 2 non-walls where you have pressure nodes. But the resonance frequency is the same. When Marcos and I were working on this, we got this crazy idea to ask the question, what would be the resonance frequencies of a sphere? So we have a sphere, and of course it's not a perfect sphere. It is more like this. And it has a diameter. I call it capital D. And the diameter is about 28.5 centimeters. Uncertainty is only a few millimeters. And so we got this crazy idea to put a speaker there, just like we did with the box, and to have a microphone inside, and then to see if we increase the frequency of the speaker, whether we could predict and actually confirm the resonance frequencies of the motion of the air inside this box. And so I said to Marcos, I know the answer. It's easy. It's a trivial problem. If this were a perfect sphere, then clearly the wall here must become a pressure antinode. A complete sphere must become a pressure antinode because there must be spherical symmetry. A sphere is a sphere, right? There must be spherical symmetry. You cannot have an antinode here and a node here because nature doesn't know the difference between upstairs, downstairs, left and right. So it must be a complete antinode sphere. But this center must then also be an antinode. Because if the air flows away and pushes onto the wall and then sucks onto the wall, it must always come back there. So the center itself must also become a pressure antinode. Knowing that, I said to Marcos, well, that means that lambda must be 28.5 centimeters, because from node to node to node is one whole wavelength. And so I made the prediction that the frequency f, which of course is the speed of sound divided by lambda, I made the prediction that that would be 340 divided by 0.285, and that is something like 1190 hertz. And I even made the prediction what the second harmonic would be. You must again add a nodal sphere. An antinodal sphere. Another antinodal sphere where the pressure reaches maximum, minimum, maximum, minimum. Because of the spherical symmetry. And so that means that now the diameter is twice the wavelength. So the wavelength is now half that value. Because from here to here to here is one wavelength, from here to here, the same wavelength. And so I predicted that the second harmonic would be twice this high. And so we set it up. And full of expectation, I said to Marcos, why don't we just start the system somewhere at 800 hertz, and then we'll find these resonances. And Marcos, a little bit more cautious than I am, he said, well, let's start a little lower. I said, well, why waste our time? He said, well, let's start low. Let's start at 45 hertz. That's what he did. You will see here the frequency of the speaker, which is mounted there. And you will then see there, if that works, you will see the... Oh boy, Marcos, it does work. And you will see there at the bottom the driver, which is the speaker, and you will see at the top, you see the response of the microphone, which is inside. Oh, sorry for that. Thank you. And so we started to slowly increase the frequency, which I thought was going to be a complete waste of time. 45 hertz, 50 hertz, 58 hertz. Oh, I forgot to turn on the microphone. Thank you, Marcos. Would have been no resonance at all. Okay, so let's go back to the 45 then. 48, 51, 52, 53, 56, 58, 60, and there is, at 61 hertz, an unbelievable resonance. I couldn't believe my eyes. I said, this is nonsense. This cannot be. It's impossible. How can you have a 60 hertz resonance frequency? What is wrong with my reasoning? Well, we were staring at each other in disbelief, and so we went on. And we said, well, I said to him, you know the 60 hertz are the lights in the building. That's what you pick up. It's some pickup, some crazy pickup. It's not a sound resonance. Whenever you see 60 hertz in Europe, in the United States, it's pickup. If you see 50 hertz in Europe, you know it is some pickup. So I was willing to forget about it. In any case, we went on and we were trying to find the other frequencies. So I will quickly now try to go to much higher values. So I go in coarse steps and see where the first one is. I was hoping to see the 1190. And then now it's 600, 700. I will now go a little slower. So watch, you see the frequency at the lower signal is increasing, much higher than it was before. And here, we're actually beginning to hear it. We're getting close to a resonance. And so, the 61 made me sick in my stomach. And I was not all too happy with 787 hertz. And so I insisted to at least start looking for the 1190. And so we started looking for the 1190. And I was beginning to be happy because I think it's coming up there, I think it's coming up there. And it fell a little short, but not embarrassingly short. 1164. I went home, and I couldn't sleep that night. I couldn't sleep. 60 hertz is absurd. Keep in mind that anything that is this size, what am I doing? I turned off the microphone. Anything that is that size cannot have such a low frequency. I didn't sleep the first night, I didn't sleep the second night, and then the third night, I woke up. And then I remembered, when I was your age, when I was a student in college, that one day I had a little flask like this, and I was blowing air past it. And I said to myself, what? Something 10 centimeters in size? You expect resonance frequencies of the order of the speed of sound divided by the length, that is 3 kilohertz. This is nowhere near 3 kilohertz. And all of a sudden that image came back to me. And I remember what I did. I said there has to be an explanation for that. So I went to the library. I looked in books, couldn't find a solution. Went to the library, found an article in the library. And that article told me what the resonance was. This one. Only one resonance, no harmonics, provided that you know all dimensions. You have to know D, you have to know L, which in our case, L is 99.5 centimeters, with an uncertainty of about 3 millimeters, and you have to know this D, which in our case is 5.5 centimeters, with an uncertainty of maybe 1 millimeter. I did my homework, I turned the crank, I went to the Hayden Library the next day. I found an article, maybe not the same that I found 50 years ago, but I found the article with the same solution. I plugged in the numbers. What do I find? 62 hertz. And I was very happy. I had recovered what I had lost 50 years ago. Now you are now at about the same age that I was then. And I want to present this to you as a challenge, something that goes a little bit beyond the standard textbooks. If you present me before December 7 with a proper solution for the 61 hertz, I will generously reward you with extra credit for 803. I am not too worried about the 787. The reason for that is it is not a perfect sphere. There is no doubt in my mind, if that had been a perfect sphere, if this thing had not been there, you would not have seen the 61, which is true, you would not have seen the 787. But the opening makes it very difficult to calculate. In fact, it's not even so bad that my 1164 does show up, where my prediction was 1190, but I'm not even sure whether that is really the one that I predicted. In any case, it's the 61 that is the bizarre one. And it has no resonances, there's only one answer. There's only one resonance frequency, no harmonics. I will be here over the weekend to help you prepare for your exam if you need me. I will make half-hour appointments. You will have to indicate what you want to discuss with me, and I will then agree on a time with you. I wish you luck, and I will see you then on Tuesday.